Okay, I don't see Austin or Jaron. Is that right?
Just in the last class.
Huh? Yeah, I'm starting now. Okay. We have, there's Jaron. Magnetic force. I actually have a picture to go with this and everything. We're going to talk about the forces caused by magnetic fields. So, first we've talked about the electric field, then we talked about the magnetic field, and I said the magnetic field was more complicated than the electric field as it relates to force. It causes a torque. We will at no point talk about the force between two magnets. We will only talk about the force on charge moving in a magnetic field. And that's for the simple reason of difficulty. We don't want to try to do things that are too difficult. So the magnetic force on a charge moving in a magnetic field depends not just on the charge and the strength of the magnetic field, but also on the direction in which the charge is moving and the direction of the magnetic field. So the actual equation, and I'm going to write it here, we'll see it more carefully coming up, but I just wanted to have it here. It's a vector, QV cross B. I don't think we've done cross products yet, have we? Oh wait, yeah, we did. We did torques. And torques used a cross product. The cross product was multiplying the perpendicular parts. And it gives you not just a magnitude, but also a direction to your answer. And so we're going to go through and work on the cross product again, because it's important here. If you do the magnitude of the force is equal to the magnitude of the charge multiplied by the speed multiplied by the magnetic field multiplied by sine of the angle between the speed and the magnetic field. So the lower equation is just the magnitude. The upper equation gives you the magnitude and the direction. And we will use our right-hand rule to get the directions. So let's look at, well, there's only one thing here that I haven't already said, and that's that the direction of the force on a moving charged particle is always perpendicular to the velocity of the particle. It's also always perpendicular to the magnetic field. So we say it's mutually perpendicular to the magnetic field and to the velocity. That actually comes out just with the cross product. So here is a quick slide on how to calculate that magnitude. So we have a charged particle with charge value q traveling with velocity vector v, the red arrow there, and it's in a region with a magnetic field B with the orangish arrow. Speaking of orange, congratulations to you Bronco fans. As much as it pains me to say so, it was a well-deserved victory. To calculate the force, I have to find the product of the perpendicular components of the velocity and magnetic field. And when you say the perpendicular components, you could easily say, well, am I looking for one's perpendicular velocity or perpendicular to magnetic field? And the answer is it doesn't matter. Choose one. So this shows two pictures. The first one is saying, okay, let's take the magnetic field and find the component of the, hey, that picture don't look right. I got to look at this again. I want the portion of the magnetic field that's perpendicular to V, or the portion of the, I've got to change colors here. The portion of the velocity that's perpendicular to B. Oh, that's what they did. Okay. So this here is the portion of the velocity that's perpendicular to B. I was looking at the picture and lost track of what they're doing. So here this is V perpendicular equals V sine theta. I should have realized from that. The other one is B perpendicular, the magnetic field perpendicular velocity, is equal to B sine theta. In both cases, if you take B times V perpendicular, that's equal to BV sine theta. And if I take B perpendicular times V, that's B sine theta V. They're the same thing. So it doesn't matter which one you're taking the perpendicular to, just choose one. Now direction, units first, then direction. Last class period I said magnetic field has units of Tesla. And then I said, and we'll worry about what the actual components of a Tesla are later. Here's where they come up. Now that we have an equation for force, the magnitude of force is equal to magnitude of charge, VB. If I look at the units for that, my units are going to be newtons equals coulombs, meters per second, Teslas. So solving that for what a Tesla is, a Tesla must be equal to a Newton per coulomb meter per second, or a Newton second per coulomb meter. So that is the standard unit of magnetic field. Now you might notice up above the work that I did with the computer, I have Newton over ampere meter. Why would I have Newton over ampere meter? An ampere is a coulomb per second, and that's the fundamental unit. The coulomb is a derived unit. The ampere is the fundamental unit. So putting it in terms of fundamental units, I would have to put, well, if I'm going to use fundamental units, I have to also use the a Newton is a kilogram meter per second squared. So putting in fundamental units, there's the Newton. There's a coulomb. A coulomb is an ampere times a second. And now I can cancel my meters, cancel, let's see, seconds, cancel 1 second, and that's kilogram per ampere times seconds squared. So that is putting it in terms of the base SI units. So the Tesla is clearly a derived unit, and obviously a second squared has no physical meaning. And so we just are happy to say a Tesla and not worry about these underlying units, as long as we know that it is based on underlying units. So that's what the unit of magnetic field comes down to being. Now the direction. So a review of cross products. We covered these first semester, but a lot of people didn't remember them from their algebra classes, or it would be linear algebra, and probably don't remember from first semester or second semester. So this here is how we write a cross product, and it means the product of perpendicular components with direction. So the cross product is a vector product because the result is a vector. It has both a magnitude and a direction. And in calculating this, we just saw from 2 slides ago, it doesn't matter if we do A perpendicular B or A times B perpendicular. They're both going to come out to have a magnitude of AB sine theta. But the direction matters. If you do A cross B, the direction is the opposite from the direction if you did B cross A. So when you're doing cross products, you have to pay attention to which one's first and which one's second. It's not like multiplication where you can put them in either order. Order matters here. So let's get right to the right-hand rule. And as we said first semester, you have to use the right hand. You simply can't use the left hand or you'll get the opposite result. Now, one student came to me and said, you know, I was reading in a resource and it said use the right-hand rule for this and the left-hand rule for that. It's possible to do that, but to me that adds more confusion, and we don't need more confusion. We need more simplicity and understanding. So we're only going to deal with a right-hand rule. And the idea of the right-hand rule is you can take your right hand and make it so your thumb, your index finger, and your middle finger are all mutually perpendicular. Right? So don't do things like this, because then my thumb and index finger are not perpendicular. I need them to be mutually perpendicular. And then when you use the right-hand rule, you always start by making your index finger point the direction of the first item in your cross product. So in this example, my first item is pointing up and to the right. So I'm going to make my index finger point up and to the right. And I'm going to keep my hand oriented like this in terms of the index finger. I can still rotate like this. That's keeping the index finger oriented the same. Then I position my hand so I can bend my middle fingers to point in the direction of B. So like this, I can bend my middle fingers to point in the direction of B. If I went like this, I can't bend my middle fingers to point in the direction of B, right? I can only bend them through that range. Now I know some people can pull their middle finger back. Don't do that. Your middle finger needs to be on the palm side of your index finger, not the other side. So I have my index finger like that, middle finger like this. My thumb points the direction of the answer if I'm using my right hand. So what direction is the cross product between A and B in this picture? It's coming up out of the page. Now, let's just do it wrong. Let's take my left hand and use the same definitions, but use my left hand. So if I take my left hand and point my fingers in that direction, I can do that. Orient my hand so I can bend my middle finger to point in the direction of B. And my thumb is going in. I got the opposite direction with the left hand. So a left hand rule gives you the reverse direction, which is why you can talk about, okay, let's use the left hand rule here, the right hand rule here, but that just muddles things up, I think. So we're always going to use the right hand. You can see you get the opposite direction with the left hand. That's why it's important to remember right hand, the right hand rule. One more thing on this. What if I reversed B and A? I said that if you reversed it, it should change the direction, right? So let's do that. If I'm going to do B cross A, what direction do I need to point my index finger? I need to point it down like this. And then I need to orient my hand so I can bend my fingers to point in the direction of A. So I need to go like this so my fingers can bend the direction of A. And my thumb points into the screen or into the paper, which was the opposite direction. You're going to have to do this a fair amount in this section of physics because the magnetic force relies on a cross product and you need to find the directions. Any questions on how to do the cross product for direction? How about the cross product for magnitude? Okay, then let's go ahead and try putting these things together. First, just notation. In many cases, we are going to have a situation where I'm going to say the magnetic field is going into my paper or out of my paper. And so we use these symbols to indicate in or out. And the theory behind them is it's an arrow. And so here you're looking at the point of the arrow, so it's coming out toward you. Here you're looking at the tail of the arrow, so you see the fletchings of the arrow as it's flying away from you. So there's actually somewhat a reason for how we have those symbols. So I will always do the ones that I marked here, circle with either a dot in it or an X in it. Apparently there are some sources that just use the dot or the X without the circle. So I will indicate fields if they're going into or out of the paper using those symbols, or directions of flight, or currents. Okay, basic things to do when calculating magnetic force. Actually, I have this on another slide. But calculate the magnitude separate from the direction. And in fact, just put an absolute value sign on that Q. Use the magnitude of the charge to find the magnitude of the force. So you're going to have a positive value. Use the right-hand rule to find the direction of V cross B. So just use the right-hand rule on V cross B. And then if Q is negative, you have to reverse the direction, because you have negative in the direction you just found. So find the magnitude, it'll be a positive number. Find the direction using the right-hand rule for V cross B, and if Q is negative, then reverse the direction because Q was negative. So here is my actual step-by-step process. It comes from a different textbook, but I'm going to claim it as my own. So the magnetic force is 0 in 3 situations. It's always useful to look for those 3 situations because you can make things quicker by recognizing, oh, that's a 0. So if the particle is stationary, remember, magnetic force is equal to Q V cross B. So if V is 0, then there's no force. So an electron just sitting in a magnetic field has no force on it due to the magnetic field. Part C, if the magnetic field is 0, once again, you're going to have no force. Pretty clear, no magnetic field, no magnetic force. And then the middle one, if the velocity is parallel to the magnetic field, so there's no perpendicular components, you have no force. So if I have an electron traveling parallel to the magnetic field, there's no force on it. It travels free of force. So those are 3 things to look for just because they're quick. If none of those are the case, then start by determining the angle between the velocity and the magnetic field. Then calculate the magnitude of the force, like I just said. Use the absolute value of charge, so you just have a positive value for the force. Then determine the direction of the cross product. And finally, if the charge is negative, you have to reverse the direction. So those are, 4 steps to finding the force of a charge moving in a magnetic field. Question? No? Okay. So let's take a practical look at this. I believe I have a picture of the Earth here. Nope, I have a clicker question first. 3 clicker questions first, then a picture of the Earth. A positive charge travels east. Now, I'm going to help you out with the figure here. North, south, east, west. So I have a positive charge that's traveling with that velocity. The magnetic field points down, so the magnetic field is going to be like that. What direction is the force on the charge?
In and out, you mean like where like a z-axis would be?
Where do you see in and out?
I mean up and down, sorry.
Okay, up and down. Okay, we have 3-dimensional space. So north, south, east, west is horizontal directions, and then up is going up out of the earth, down is going down into the earth. Okay. All right, everybody's answered. We will have you sit with your partners and discuss this. There was no majority, there was a plurality. Every answer got one call. So talk to people around you. If everybody around you had the same answer, find somebody who had a different answer so you can get some variations of ideas.
Back to the hand thing.
Okay. I've been asked to go back to...
It's on the computer here. If this is easier for people, we can look at the computer.
Yeah, go ahead and do that because I want people to be able to review with questions.
Yeah, so this is like some east. North is up.
Okay, I was wondering. I was like,
And they got cable. Let's get it right. So if you start. So when it's west,
yeah, B is the magnetic field.
oh, okay, the magnetic field. Oh, what's magnetic field goes down?
Yeah, down to the east.
So it would be north. Okay, I was thinking about it. Magnetic field.
So, ready? B magnetic field, right?
I was thinking about it as this was
So down into the space.
North and south.
Right? Okay, because up this way, down is that way. So into the sky, right? Our thing is moving east. Right? So that's where I'm pointing, so our palm facing north. That's the direction.
That's right, I saw that.
So then, I had it.
Okay, we'll re-poll it, and if we don't get unanimous agreement, Lindsay's going to explain it to you. Michael. Okay. After everybody discussed it, so Lindsay,
I didn't bring it because he specifically said he was going to get the right.
I got the right answer. I didn't.
No, okay. So I got the right answer, only opposite the first time because I was using my left hand. I don't know why, but.
no, I didn't ask you to tell them why you got it wrong. How was
Okay.
that?
So use your right hand and you point it and your next finger at the V. And then you curl your fingers towards B. Bam.
Bam, and then she rotates her hand over.
It's pointing down. How is it? How did you get there?
Okay, so taking this as our directions. So our horizontal plane is going to be looking like this, which makes out this direction and in that direction, right? So I'm using this for my directions. So I take my right hand and I take my index finger and I put it, since it's Q, V cross B, V is the first one, so I put my index finger in the direction of V, so my index finger is pointing that direction. Now I've got to keep my hand with my index finger pointing that direction, but I can rotate this way. Then I need to point my middle finger So it's pointing the direction of B. That's the X's for the fletchings of the arrow, so it's pointing in. So I have to have it like this. My thumb points the direction of V cross B. My thumb was pointing north. And so I have north, and then for the last check, what's the last check? Whether it's a negative or positive charge. It was a positive charge, so it stays that way. If it had been a negative charge, it would have flipped it. Does that answer, Dixon? Maybe.
What are your fingers? Okay, never mind. I got it.
Okay, another clicker question. Remember I said there's 3 of them here? Don't answer yet. Now you can answer. Now it's a negative charge. Everything else is the same. Just change it from a positive charge to a negative charge. Excellent. You just change it from a positive to a negative. It flips the direction, so instead of going north, it was going south. Okay, our last of this set of questions. A positive charge travels east in a region where the magnetic field points east. So now I've changed it so the magnetic field is east.
Really just don't have the answer. Yeah.
Okay. Still waiting on Sally and Helena.
I can explain this. I don't know. Or did we get? Because we did the
Okay. Our answers were 17 with no force and 1 with north. Wait.
Don't ask.
Okay. The 17 are correct. Why are they correct? Because there's no perpendicular portions. Cross products only give you a non-zero answer if you have something that's partially perpendicular at least. When they're parallel, it's always 0. One of our simple cases, you don't have to sit here and try to bend your fingers in funny directions. You just say, 0. Hey, look, it's an example on it's a better example now. Suppose a proton is moving straight down directly toward the equator. So in this picture you see my proton moving straight toward the equator. Which part of the Earth is at the top here? The north or south geographic pole?
North geographic.
Okay, I hear people saying north. Why do you say the North Pole? Yeah. It's more complicated than it seems because the North Geographic Pole is where the North Pole of the magnetic field points to, but magnetic fields come out of north and go into south, so it's a south magnetic pole. Got that whole backward thing going on. Because the magnetic field lines are coming into it. That's how we define north. So that's the North Pole. We have a proton coming in. What is the direction of the magnetic force on the proton due to the Earth's magnetic field? So, just zooming in on our picture here. Oh,
Question.
yeah, question.
Will this stuff be on
protect?
No, it will not.
Okay. Just preparing myself.
What direction is the force?
South.
Okay, I have an answer of south. At least I have an answer. Let's check now and see if he's right. So, following our steps, I first am just going to do V cross B. He decided he's wrong. My V is pointing into the earth. My B is pointing what way? So I'm going to rotate my hand over. And my thumb is pointing into the page. What direction would that be? That would be east. It's going to define a circle eventually, but right now, east. So that means that I have my forces east. Now, there was one more step. What was the one more step? I'll answer your question in a second. What was the one last step? If it's a positive or negative charge, I have to check, but it was a positive, so it's still east. What was your question, Lindsay?
Okay, why couldn't I curl my fingers under?
Why couldn't you curl your fingers under? Okay, so you started with you're good with your fingers pointing this way to start with, right?
Yeah.
And then the magnetic field is going this direction. So at this point,
Oh.
I need the magnetic field to point that way.
Oh, okay.
And then the last part about getting east required me to essentially take a flat compass and put it over this point to determine, yeah, that direction would be east. Okay, so we've got the first part answered. It's going to be an east force. Second question, how does the Earth's magnetic field protect us from solar radiation, from charged particle solar radiation, not from electromagnetic field solar radiation? She's still answering the next question. No, not you. Anne's still answering the next question. A positive charge will be deviating what direction? It has a force to the east, and hence it's going to be deviated east, because Newton's second law. If it was a negative charge, what would happen? It would be west. So the charges are going to be separated if we're at the equator. Now, what Anna's been asking, or answering, not asking, is what happens if that same proton comes in here instead. Now, if we do our same work, index finger like this for V, middle finger pointing at an angle like that, force is the same, right? But because these aren't perpendicular, it's still going to maintain some velocity that's parallel to this. And so what's going to happen is it's going to make it spiral around the magnetic field lines. And so if the charged particles come not at the equator, but somewhere closer to the north or south poles, they will then spiral around the magnetic field lines and follow them in to the poles. Following them into the poles means you can have a lot of charged particles coming in at the poles. And that's what gives us our aurora borealis and aurora australis. They are directed to the poles because the charged particles follow those magnetic field lines, and the magnetic field lines come in toward the poles. And believe it or not, this was actually a question I was given on my oral exams for getting my doctorate. This is the oral exam part of the prelims. 4 5-hour exams on physics. Yeah, it was totally fun, followed by an oral exam. And my professor asked me about how you could make a microscope by using this phenomenon. By having magnetic fields expand outward, you have electrons that are coming off the surface and expand outward, and you magnify. Oh, was there a third question? Where on Earth's surface is the shielding least effective? Well, yeah, the top or the bottom, right. So, at a certain place on the Earth's magnetic field, we have a magnetic field of 0.050 milliteslas. The reason we use Gauss a lot is because We put that in Gauss, it's just a half a Gauss instead of 0.05 milliteslas. So we have this magnetic field. The field direction is 70 degrees below horizontal from north. So find the magnetic force on an oxygen ion moving due east at 250 meters per second. What's the magnitude of the force going to be? Well, for the magnitude, we just do Q, VB, sine of the angle between the two. So I need to know what that angle was. Remember, that was the first, the first step was if it's 0, do that 0 right away. But it's not a 0 situation. So the second step is find what that angle is. So what's the angle between east and 70 degrees below north? Say it louder.
Was it 20 degrees?
Not 20 degrees. I will use my arms to illustrate. Here's 70 degrees below north. Here is east. What's the angle between those? It's 90 degrees. One's in the north vertical plane, and one is in the east direction. The east direction is perpendicular to the north vertical plane. So the angle between them is 90 degrees. So theta is 90 degrees, hence this is just going to be the magnitude of the charge, 1.60 times 10 minus 19 coulombs. That's absolute value sign, times the speed of 250 meters per second, multiplied by the magnetic field of 5.0 times 10 to the minus 5 Teslas. Somebody with a calculator, what do we get for that force? Excuse me? Oh, yes, 10 to the minus 5. Thank you. Two. Okay, 2.0 times 10 to the minus 21 newtons is what my esteemed student tells me is the magnitude of the force. Now, as far as the direction goes, what direction is that force? We have our index finger is pointing east. Our middle finger, so east. Being realistic, east is that way. Nope, that way. Index finger is pointing east. My middle finger is pointing north, but 20 degrees down from north. So like this. Right, 'cause north is that way. So what direction is my thumb pointing?
70 degrees down. Right?
Yeah, this is 70 degrees. I'm sorry, I did the math already.
Yeah, so it's 20 degrees.
It's 20 degrees above horizontal north. So it's northerly at 20 degrees above north. So there's my force vector. Now we're told to compare the magnitude to the force of gravity, which is given 5.2 times 10 to the minus 25th newtons. How is this magnetic force compared to the gravitational force? It's 25,000 times stronger. So we could probably ignore gravity, right? We have one force that's 25,000 times stronger than the other. And then the electric force. Well, how big is the electric force? Ooh, this will be on the test. What's the equation for the electric force? No, because I have an electric field and a charge. What do you say, Bregan?
K, Q1, Q2.
That would be between 2-point charges. But this is between a charge and electric field.
It's just KQ. And the point charge is the big Q?
It's just QE. Right, that's the point of the electric field. Remember, the electric field now is the easy one. The magnetic field, clearly, you can see why it's harder. No right-hand rules to worry about. The electric field is downward. It's an electron. So, I put 20 degrees above north. I made a mistake. What was my mistake? It's a negative charge, so I have to switch the direction. So it's 20 degrees below south. Right, I did the force as if it was positive, but this is a negative ion. And so I have to look at that. Okay, so now this one here, this can be 1.602 times 10 to the minus 19 coulombs. Negative sign, because I'm not using absolute value. And then 150 newtons per coulomb down. So what do I get when I multiply those two together? Notice minus down makes it up. So I put it as up. So in this case, the electric force is actually about 10,000 times stronger than the magnetic force. I believe we did all the calculations correct here. It looked right. So when you're looking at this, you would say, well, the electric force is going to be the most important force on this oxygen ion because it's moving relatively slowly. Now, this is a realistic problem. It's realistic. The oxygen molecules in the atmosphere are really moving somewhere around that speed. And so for those, gravity is really not going to be much effect on them at all. It's the Earth's electric field that's going to be the biggest effect. That's what keeps them above the surface of the Earth instead of just falling to the Earth. Yeah, good for us, right? We like to breathe. Okay, I'm going to change it out of being zoomed in. That's annoying to me.
Quick question.
Yeah.
Wouldn't that just make them all go up? I mean, like, you say, well, we get to breathe, but what's...
I haven't looked at the electric field strength and how it varies with distance. Obviously, if it was just a point charge, it'd be 1 over r squared. But I assume that at some point, you're going to have a net force down. Otherwise, yeah, we'd lose it. Of course, this is also ionized. If it's neutral, then it's just going to be gravity pulling it down. So we have to have the balance with those as well. It's complicated, and I'm not someone who studied it. Okay, coming back to the idea that Anne was talking about the charge spiraling. If I have a charge moving in a uniform magnetic field, that charge will have a force that's always perpendicular to its velocity. So if the velocity is perpendicular to the magnetic field, then the charge will do circles because it has a force perpendicular velocity. That's the whole situation that makes things go in a circle. A force perpendicular velocity only changes direction. It's a steering force. It doesn't speed it up or slow it down. So the magnetic force won't speed up or slow down our particles, just changes their directions. And that brings us a whole slew of applications. So first we'll start with that circular motion. If I have a charge with speed v, moving in a magnetic field B, that's perpendicular, then the magnitude of the force is QVB. So force net is equal to QVB. But according to Newton's second law, the force net should be equal to mass times centripetal acceleration, which is mv squared over r. So now I can solve this to find something like what's the radius going to be as a function of these other variables. So if I solve this for r, one of those v's will cancel, and I'm left with a circular path with radius equal to mass to charge ratio times v over b. Why did I say mass to charge ratio? Because in most cases that's all we know is the mass to charge ratio. We take other things to move forward from that. So we can determine the mass to charge ratio if we know what the speed is in the magnetic field and we measure the radius. That is exactly what we do in some of our simple mass spectrometers. So a simple mass spectrometer, you have some source, put them through an accelerating voltage so they're going faster. Number one is you want to know what their speed is. If they're coming out slow, like, say they're going somewhere between 0 and 5 meters per second, and then you speed them up to 250, that means they're going between 240 or 250 and 255. You can be pretty small in your uncertainty in velocity as a percentage. And of course 250 is the slow speed, you'd go much faster. So you have this stage here to make them go fast. And so you know what their speed is. And then you shoot them to a region with a constant magnetic field and you measure the radius. And since we just saw that radius is equal to the mass per charge V over B, then I could also solve that for the mass. Mass is equal to radius times B. And I get that relationship. I just make sure I did my math right. I think that's right. So the mass is just proportional to the radius, and the proportionality depends on the strength of the magnetic field, the velocity the particle has, and the charge state. So that's a very simple mass spectrometer. When you have like a residual gas analyzer, that's usually what they have in them. It's just something like that. A practical example that we don't have time to do. A mass spectrometer has lithium 6 and lithium 7. What's the difference between lithium 6 and lithium 7? One has an extra neutron, so the masses are different. They're both +1, so they have the same charge, but their masses are different. And so we're going to want to use this mass spectrometer to measure the masses. And of course, we'll measure the radius, and from the radius determine what the mass is. Now the problem is simply if the radius of the orbit for the lithium-6 is 8.4, what is it for the lithium-7? We actually can do this because our equation was radius is equal to if everything is the same, and if I change this mass by 1, ratio of 7 to 6, then my answer is going to go up by the same ratio of 7 to 6. So we actually do have time because that was a very simple problem. Okay, we have a test tomorrow in lab period. There are questions at the very bottom of Moodle from the different chapters. There are only 3 chapters from the textbook where I made the questions from. So I renumbered those 3 chapters. So it says Physics 152 instead of 151, and then chapters, so you know which ones to look at. We'll be covering electric charge, electric fields, electric force, electric potential, potential energy, capacitors, electric circuits, resistors, Kirchhoff's laws. Excuse me? Austin sent me an email saying there weren't, but at least the ones I checked, there were.
There wasn't. There wasn't.
So which one doesn't have them? Because
The exam one. Talking about the question.
oh, okay, you're talking about the okay. I was only talking about the practice questions. Okay, so
Practice problems are also, there's only like 2 of them that have questions. 2 chapters that include questions.
I'll have to look at it again.
Yeah.
I looked at all of them last night, though. Anyway, I'll look again.
It was electromagnetic stuff